Hi. So previously in this series, we discussed two different kinds of games, right? So the first one was the strategic game or simultaneously move game, and another one was the extensive form game, where we the players they have some orders, they play their moves in order. Um, Someone plays first, then someone plays second. So those are some games that have perfect information. Okay, so now we are going to introduce other kinds of games where we have some imperfect information or incomplete information. Okay, and so how do we model the imperfect information? Basically, we introduce some concept called state of the world or state of nature, which is just some random variable, and the players they might fully observe that, or some players might not observe that at all, or more generally, the players they might just have some partial observation on those signals on those states by some signals. Okay, so this is how we model the information in the strategic or dynamic games. Okay, so before we go further into the dynamic games, so let's take a look at the simultaneous move game or strategy games with imperfect information, and which is just called Bayesian games. Okay, so the name of Bayesian game comes from the place that we will see that we'll use the base rule to update the belief from the prior to a posterior. So the later we'll see the meaning of those terms, but essentially the prior belief is just some belief or some knowledge or a guess on this state nature before the game starts, right? And the posterior belief would be some new belief or updated belief using the base rule to update the belief from the prior to the posterior. Okay, so after the realization of the state. Okay, so those would be the key parts that we're going to introduce into the games. So let's before that, let's have some notations for us to follow. Okay, so we often wish to model the situations where some of the parties are not certain of the features or characteristics of some of the other parties in the game, right? So, and this is the Bayesian game, and so previously in a strategic game, so the two important parts are the set of players and right, and a action profile AI, right, for the players. So here we like we just mentioned, so we want to model this uncertainty or this the imperfect information in this context. So how do we do that? So simply we introduce some like using this omega or some other letters to denote this state nature, okay, or a state of the world. So those are the same thing. Okay, so this is something that players might or might not observe or partially observe, right, using some signal from that. So, and normally we assume that this omega, this space is this set is finite. Okay, and player, so each player I might have some prior belief. Okay, let's say use this pi, little pi. Okay, so this prior belief would be an element in the set of all distributions over this omega. Okay, so we use this data to denote the set of all distributions over that. Okay, so this is just a probability, right? So a probability measure, and normally the different players they could have different prior beliefs. right? So in a game with two players, the two players, they might not have exactly the same prior belief, and of course they might not have the same posterior beliefs. Okay, so in any given play of the game, some state nature omega is realized in the game, right? So before the state is realized, then this prior belief is held by the any player, right? So later we'll also introduce this signal function, okay, so which generates some signal from the state, okay, and that signal might be fully revealing signal, or just maybe a nonsense, or maybe a general signal like between 0 and 1, which is somewhat helpful for the players who know about the state, right? So we use this tau I, okay, and take this omega as the input, which is a signal function for player I, okay. So being the signal that player I could observe before choosing the player's own action, right? And given that the state nature is omega, okay. So and we denote this capital Ti, okay, to be the set of all possible values of omega I, okay. Set of all all possible values of tau I, not omega, okay. And sometimes we could refer to this as the set of all signals, or we could call it as the set of types, okay. So this is exactly the equivalent concept, or it has the same meaning as the signal, okay. So these types could sometimes when we're reading the paper, we could see that there are some high type or low types agents, right? So that essentially means that the agent receives some signal with high signal or low signal, okay. So that would be having the same meaning exactly, okay. So if the player I received the signal Ti, okay, then this player deduces that the state is in the set, okay. Then this has to be like an infer, right? So infers that the state is in the set, okay. So omega is in, so we use this inverse function, right? So it means that, so we know that when the agent observes some tau I, some Ti, some signal, then it might come from the state omega, or it might come from other state, okay. So that's why this agent needs to infer this true omega, the true state, right? Okay. Good. So in this case, and normally here, because we're using the Bayes rule, so that's why it's called the Bayesian game, right? So, and this agent's posterior belief, okay, posterior belief about this state, that state has been realized, assigns to each state omega to some probability, okay. So this posterior belief would be also be some probability, of course. So this would be just applying the Bayes rule, okay. So this Pi omega. So this is a bit confusing, okay. So this is actually the numerator of the Bayes rule, right? So it is the probability of having this receiving this signal Ti, and also having the state as omega, okay. So this is a joint probability, right? And as the numerator, and the denominator would be the unconditional probability of sending the the signalization or the signals, right? So this would be the pi and tau I inverse ti. Okay, so it means that the denominator here means that all those possible, so it is divided by all those possible, the sum of those probability sending this signal realization or this signal ti. Okay, so it might come from omega or omega 1, omega 2, or something else, but it has to be some signal, be some state that could send out this signal ti. Okay, so then we use this fraction or this ratio to simply represent the probability of if the state is omega and then it sends out this ti and divided by all those probable cases, right? Okay, and that's just an application of the Bayes rule. Okay, so if this is the positive belief, if omega, of course, it's an element of all those possible cases, right? And the probability 0 otherwise. Okay, so that is the probability of omega conditional on this this thing here. Okay, so but normally this would be positive, right? Okay. And of course, when we're saying that we apply the Bayes rule whenever possible, it means that it has to be a positive number, right? So if it is 0, then we cannot apply this Bayes rule. Okay. So as in the textbook, so as an example, if tau I omega, okay, so if it is a fully revealed, like we just mentioned, right? So if stays omega, then the signal is omega. So if it's a fully revealing signal for all omega, then I has full information about the state, right? So there's no uncertainty for player I. Okay. And alternatively, if okay, this is also useful. So if omega is the cross product of all those TIs, and for each player I, the probability measure PI is a product measure on omega, and we also have this fully revealed signal. Then player signals are independent. Okay, this is also useful result. Players signals are independent. Okay, and player I, in this case, doesn't learn from this player's own signal about the other player's information, right? I doesn't know or doesn't learn, okay, from own signal about the other information. Okay, good. So those would be just some little useful results. Okay, so before we formally define a Bayesian game using the parts we just introduced, so we know that in a strategic game, each player cares about the action profile, right? So which is some outcome or outcome of the game. So in addition, the players might also care about the stable nature here, right? If there is some. So now, even if the players know that action taken by any other player in each state nature, in each realization of that, the player might be uncertain about the true state, right? So So in other words, the players, they're not certain about the pair, including the action and the state omega. Okay, that will be realized given any action that the player takes, because the player has the players, they have the imperfect information about the state nature. Okay, so how do we introduce this formally? We simply use a concept called lotteries, and which is just some probability distribution. Okay, so okay, before so we include this preference relations. Those are the relations over the lotteries. Okay, preference relations over lotteries. So those are just some probability distributions. Okay. Okay, so this has to be a cross omega. Okay. So before in the previously in the strategic games, this just the cross of all the a's, right? So here we have the omegas. Okay, good. Now we're good to start from defining the Bayesian game. Okay, a Bayesian game. Okay, it is a tuple including a lot of things. Okay, so first is the set of players, and we know that we don't have to write the note for that. And omega, the set of states, of course we know that also already, and the action profile for each player I. Okay, and a finite set Ti, which is the set of signals that might be observed by player I. Okay, and a function, okay, tau I. So this tau I, okay, so this Ti is the set of signals might or might not be observed by player I. And this tau I is just a function from omega to Ti. Okay. So this is the signal function. Okay. Good. And a probability measure, Pi, which is the prior belief. Okay. Just some number between 0 and 1. Prior belief of player I, for which we have some requirements for that. So this is a positive number, Pi, and taking this signal function inverse given some signal Ti, right? So this is just some state, right? This is the signal, and this tau inverse will be the inverse function for the signal function, right? Okay, and this is positive probability number for all those Ti's. Okay, and what else? We also have a preference relation, okay, and that we just mentioned. So this would be something defined over the lottery, right? This is the preference relation on the set of probability measures over, okay, over A cross omega. Okay, so we can just take this as in the utility functions we have both of those variables, right? The action and the state. Okay, good. And this further, this A would be the cross of all the A's for each player. Okay, good. So we notice that this definition it allows the players have heterogeneous or different prior beliefs. Okay, this is very important. Hetero or different priors. Okay, and this will be a useful note here. Okay, and those beliefs, the players' beliefs might be related, right? So they don't have to be independent. Okay. So normally they're identical, the priors. Okay, and sometimes it might be useful to assume that they have different or heterogeneous beliefs in some special problems. Okay, good. So sometimes we can also notice that a Bayesian game is described not in the terms of an underlying state space omega, but it is as a reduced form, and it's simply called as the player's types. Okay, like high type or low types. So if those would be easier for people to understand and to study. Okay, so good. So now we have the definition for a Bayesian game, and now we could try to start to define the equilibrium for a Bayesian game. Okay, so simply we adopt the Nash equilibrium and try to modify that in terms of the including those lotteries or including those probability distributions, right, over the state. Okay, so in any given player of the game, so each player knows the player's type and doesn't need to plan what to do in the hypothetical event that the player is of some other type, right? So consequently, the players, they might think that an equilibrium should be defined for each state of nature in isolation, right? So, but the problem is that in any given state, player who wishes to determine the best action might need to hold a belief, as we just mentioned, which is just a probability distribution over the state about what the other players would do in other states, right? Because players, they might be imperfectly informed by those signal functions about the state, right? And further, the formation of such belief might depend on the action that the player themselves would choose in their states, since the other players might also be imperfectly informed, right? So it essentially means that each player might be imperfectly informed about the state, and of course each player has to make the correct inference about the state. Okay. Good. So essentially, the approach to try to transfer the mass equilibrium to this context is to just multiply the utilities by the corresponding probabilities. Okay, and make this utilities as the expected utilities. Okay, so that's the key part of the transformation from those concepts. Okay, so so then we could start to try to define the Nash equilibrium for the Bayesian game. Okay, good. Okay, so let's do that. Okay, we have this tuple. Okay, to be a Bayesian game, where this we have the player set and the possible signals. Okay, so so here we refer to this. Okay, so when we're saying that the players in this game, we simply, like we just mentioned, in kind of a reduced form. So we could refer to those signals as the types, right? So here we could incorporate the types into the agents. So we can just say that there are different kinds of or different types of players. Okay, so here we simply use the notation such as the player I and a Ti. Okay, so this is representing the type Ti of player I. Okay, good. So, and the set of actions for each player, such this kind of player is AI correspondingly, right? And the set of action profiles will be just the cross product over all those players, and also across over all those types. Okay, good. And the preferences of each player are defined as follows. So first, the positive belief of player I, together with an action profile A star in this game, and it generates a lottery, okay, Li, given some action profile A star, and its Ti. This is over A cross omega. Okay, so the probability assigned by this Li to, okay, so the probability assigned by Li okay to this action, which is A star, and here we have this signal function, right, to indicate the type. This is a player and the type, right? Okay, this is for all the players, and we also have this state. Okay, so the probability assigned by this lottery to this set crossed by the action and omega, A and omega. So this is player I's positive belief that the state is omega when this player receives some signal. Okay, being the action of player in the profile. Okay, so is player I's posterior belief that state is omega when this player receives the signal, okay, Ti, A star, okay, player J, and the signal function tau J, okay, being the action of player J, tau J, okay, omega. In the profile A star, okay. Okay. Good. So so here player I, okay, Ti, okay, in the game, in the strategy game, okay, prefers the action profile A star. Okay, so here, because we have explicitly write out all those types, right? So here, we're always referring to the strategy game G star and referring to the action profile A star in the strategy game G star, okay? And profile A star to the action profile B star if and only if player I in a Bayesian game, okay, prefers the lottery Li A star Ti over the lottery Li B star Ti, right? Okay, so this helps us to formalize the preference relation in this context, right? Okay, so now we're ready to define the Nash equilibrium in a Bayesian game. Okay, Nash equilibrium in a Bayesian game. And it is called Bayesian Nash equilibrium, right? BNE. Okay, good. So a Nash equilibrium in a Bayesian game, which is a tuple n omega, ai's, ti's, tau's, and priors pi's, preference relations. Okay, so it is a Nash equilibrium of a strategic game, G star, okay, defined as follows. Okay, so the first, the set of players N is the set of all pairs, okay, I and Ti, okay, for all the I's and all the Ti's, okay, as we just mentioned. So here we write out those explicitly for all the players and for all the types of the players, okay, good. And the set of actions of each player, I and Ti, okay, is this AI. Okay, and the preference relation or the preference ordering, ITI, okay, of each player and with the type, I, Ti. This is defined as follows. So A is preferred, then B, A star is preferred, then B star in this player ITI. Okay, so this is if and only if the agent prefers the lottery, right? Okay, so here in this lottery we'll have the probability of having that outcome and the corresponding utility, right? So that would be the expected payoff. B star, Ti, okay? And this, where this Li, A star, Ti is lottery over A cross omega, that assigns this posterior probability, right? So we just derived that using the Bayes rule, that assigns pi omega over pi tau I inverse Ti to this action. Okay, A star, player J, tau J, omega, for all the J's and omega. Okay, so this is over A cross omega, right? If omega is in this tau I inverse, okay, and zero otherwise, if it doesn't apply. Okay, so intuitively, it in a Nash equilibrium of a Bayesian game, each player chooses the best action available to this player, given the signal that the player receives, and the player's belief about the safe nature, and the other player's actions that the player deduces or infers from this signal, right? So, and we notice that in order to determine whether the action profile is a Nash equilibrium of a Bayesian game, we need to know that not only how each player in a Bayesian game compares the lotteries or the expected utilities over this A cross omega, where the distribution over omega is the same. Okay, so it means that the player never needs to compare the lotteries in which this distribution is different, right? Okay, so from the perspective of Nash equilibrium, the specification of the player's preferences in the Bayesian game contains more information than that is necessary, right? So this would be a formal definition for the Bayesian Nash equilibrium and the definition for a Bayesian game. Okay, so in the next few episodes, we will follow the textbook and try to introduce some very interesting examples in Bayesian game and using the Bayesian Nash equilibrium, such as the second price auction and some other very interesting examples.